In progress.
Okay, so hello everyone, and welcome to the what is not the NCGT seminar, as written in the title. And today speaker is Mauro Mantegazza from Charles University, and he will speak about Topos theory.
Thank you. And thank you for letting me talk about Topos theory, which is a topic that I'm not really working on actively since like 8 years ago or something like that. It's a pleasure to be back. So let's start. The plan of my talk would be to start from the geometric background where Topos theory actually arose, where basically the geometric environment that was later generalized to topoi by Grothendieck. And then we'll be building topoi using the construction of Grothendieck, the so-called Grothendieck topos. We proceed by studying the categorical properties of topoi, and from those we'll get to the even more general notion of topoi, which is the elementary topos. And from then on, it will be a slow descent into madness through logic and internal logic and so on. But it will be fun, hopefully. Okay, so let's start from the geometry. The area that Topos theory wants to generalize is essentially the geometry of sheaves. So let's review what a sheaf is. We take a topological space X, and we denote by O of X the lattice of its open subsets. We can see it as a category where maps are exactly the inclusion, so there is at most one map between two objects. And we view the inclusion, yes, as morphisms. Okay. So let's start by defining what a presheaf is. Presheaf is a functor, contravariant functor from this category of opens to sets. And what it means in words is that to every open subset, we associate a set such that there is a notion of restriction, meaning that whenever there is a V included in U, we have a map from f of U to f of V, which wants to be thought of as restriction to the smaller V. So this is what a presheaf is. Examples are like the sheaf of smooth functions. For instance, if we take a smooth manifold, and to every open subset, we associate the algebra of smooth functions from U to R, then this will form a sheaf with the standard restriction. Same happens for CK, same happens in algebraic geometry with the bundle associated to a scheme, and also the presheaf of continuous functions with the compact support is a presheaf, but as we'll see, not a sheaf in general. Then you have banded function, and the last one is the most useful one probably, which is the constant sheaf, which is like trivially defined as like to every object we associate the same set S, and the restriction map is just the identity. So it's a trivial object, but it's there and can be used. Okay. And of course, we take as morphisms from a presheaf F to a presheaf B natural transformation. So for every object U, we have a function such that it commutes with restrictions, the usual. Examples, the inclusion maps between the analytical spaces and the differential, for instance, between the C-infinity algebra and the DRAM, the first grade of the DRAM complex. Okay, we denote the category of presheaves in this form, which is reminiscent of the way exponential objects are denoted, which essentially, we'll see them later in detail, but it means that we're taking the functors from the top object to the bottom object, so from OX to set, just notation. Okay. Okay, so finally a sheaf. So on a topological space, a presheaf is a sheaf if for every family U of I, and for every element of this family, we take a section f of I of big F of ui. Every time that a couple of these sections coincide on the intersection, so if every couple of the sections coincide on the intersection of their open sets, then we want there to be a unique map F on the union of the open subsets such that this F restricts to the opens. So this is the usual gluing lemma. So it's the usual thing, that just to keep it in mind. So we have open subset, we have functions defined on these such that on the intersections they have the same value, and if this happens for every couple of opens, then we can glue them together, and there exists one and only one, and this is the crucial property of sheaves. Okay, examples. We have the analytical function, the scheme, the constant one, but non-examples are the compactly supported continuous functions, because of course if we take compact functions with compact support and we sum, we put them far enough so that they live on the, like they agree on the zeros of the border, but we take a countable quantity of them, then of course the support cannot be compact, because it will not be possible to cover everything with a finite, it would not be possible to refine the covering. Same for bounded function, because of course if, for instance, on R we take the exponential map and then we consider a family of intervals, all the restrictions will be limited, but the union will not. And so there is no, so these are not sheaves. We will denote the full subcategory of sheaves over X as sheaves of X, SH of X. And now a question. So we started from a topological space. We produced the topology. So the category of open subsets. And then from this we built a categorical object. So this category of sheaves. The question is, are we able to reconstruct back X? Because it will be a way to identify spaces with categories of sheaves. But unfortunately, the answer is no, because the only data we actually used was the lattice structure of the opens of X. So if we have an isomorphism between two lattices over topological spaces, then this will induce an isomorphism on the categories of pre-sheaves that induces also restricts to an isomorphism to the categories of sheaves. And instances of two isomorphic spaces of course could be the point and any other space with more than one point that has only the total open and the empty open. These are two examples of isomorphic lattices of opens that do not come from isomorphic spaces. But the good news is that we can fully recover at least O of X. And how do we do this? And we do it with particular subobjects. So this will be an excuse to talk about subobjects, since they will come out a lot in the talk. Okay, to be precise about the notion of subobject, we say that it's an equivalence class of monomorphisms inside the main object X, where isomorphism means that they're isomorphic and that the diagram with the inclusions commutes. This essentially means that the only thing we care about is the image of these. So we don't care where it comes from, we only care how it enters in X. Then if we have a morphism, this morphism between two classes, this morphism is well defined, so it doesn't depend on the class chosen. It must be a monomorphism, because whenever a composition of maps is a monomorphism, then the first one must be a monomorphism as well. So we have basically a poset because there is at most one map as well. Okay, an example. Let's see. If we take the category of pre-sheaves or the category of sheaves, we can identify each isomorphism class with the subsheaf, which means for every object, U, G is a subset of F. So in every component, it's a subset. That's what it means. Okay, so how do we reconstruct the topology? We, in both categories, so both in pre-sheaves and sheaves, we have the constant sheaf that I defined before. So this object is the terminal set in each component. This is a sheaf, and it's terminal in both categories. If we now consider the subobjects of this one, we notice immediately that these are subobjects. So these are functors defined, pre-sheaves defined, so that it's the y of u, index for every u. Y of u in V is 1 if and only if V is included in U, otherwise it's empty. Notice that it's not by chance that I called it Y of U, because this happens to be the Yoneda embedding as well. Because in the category of O of X, there is a map if and only if V is included in U. So these are homomorphisms from V to U, essentially. Okay. So it turns out that these are exactly all possible subobjects of 1. So what happens is that sub of 1, which is a poset, which has a certain structure, is isomorphic to O of X. And this tells us that we can fully reconstruct X. We can fully reconstruct O of X, and in particular, if X is sober, which means that the opens are enough to determine every single point, in a sense. It's a separation condition, essentially, and what matters to us is that everything sane is inside, in a sense. So we have manifolds, we have schemes, and functional spaces usually. So it's everything is reasonably inside. Okay. Now it's time to dig the first step into hell. So we want to generalize this notion of covering and coverage. What do we want to generalize, though? So by what we saw from the definition of sheaves, the important notion is that something that happens at a global level could, in theory, be recovered by something that happens at a local level. So this is what we want to generalize. We want to give a notion of what does it mean for a family of arrows to cover an object so that I can recover the information of that object from the domains of these maps. But let's see in detail. So instead of O of X, we take a small category. So this will be our environment now. Every object of this category will be a place where I will be able to define sections of a pre-sheaf and then of a sheaf. What is a coverage J on this category? It's a function that assigns to every object C a collection of morphisms that we call J covering. So morphisms that we want to be covering that have codomain C. So are maps that are going into C. And we want that to be such that for every other map, and this is a very technical condition, but I will explain it better. For every map, there exists a J covering family on the domain. I think there. Let's see. I think this is a mistake. It should be J. But anyway, there should be a coverage such that if I compose this with an f, with the function f, this filters through the first, but nothing is understandable from what I said. So let's see it in action. So we take an object B and we take a family that covers B. The property that we want is that for every map F from A to B, there exists a covering family W of A such that the composition, each composition W with F factors through an arrow of B. What this wants to model is whenever, so if we think about the previous example, whenever we have an inclusion, we want a covering of the whole thing to be refinable to a covering of the smaller space. And what we do in the classical topological case is taking the intersection of the covering family with this F, so the pre-image of F. Okay, this is just the only condition that we asked to get coverage, and it's enough to allow us to define what a sheaf is. So let's see a few examples. Yeah, as I said in the topological example, we could build a canonical coverage where for every space U, a family of UIs, which since we have an arrow from UI to U, it means that UIs are subsets of U, open subsets, are such that, so this is a covering family every time that the union is the whole of U. So this is what we did before. So that's where we want to generalize. And of course, if we substitute O of X by any pre-order and every union with the joins, which are would be the co-limits in this category, then we can obtain the same. So this is already a smaller generalization. Other two, let's say, peculiar coverages that we can put on any category are the trivial one, which tells us that the only family that covers an object U will be the identity. And of course, this is sort of the most disconnected version, because we can't recover global information from anywhere else than from the global picture. So we have a total disconnection from global to local to global. Another example, which is not a single example, but a family of examples, but they all behave similarly. Whenever the zero coverage, the zero family, the empty family, sorry, covers an object U, then this is also a coverage, and we'll see what this implies. This is, in a sense, the opposite picture. So no map entering into the object will be able to recover the total information. This tells us that the sheaves are not going to be too interesting, but we'll see in detail what happens. Okay, now let's talk about the generalization of the gluing lemma, which is the amalgamation. So yeah, so our data is a pre-sheaf on a small category C to set, and yeah, okay, definition first. These are pre-sheaves on a generic category, so it's just a functor from C up to set, and whenever we have a map from W to U, then the induced map will be denoted by restriction through F. Notice that I'm not writing restriction to W here, because in general there might be more than one way to go from to restrict from U to W. In general, categories can have more than one arrow from between two objects, so it's important to specify the function instead. Okay. And now the notion of compatible family. So before, the idea of compatible family was a sequence of a family of sections defined on each element of the covering. Now here is the same. So we have an object, and we have a covering family, UI, UJ. And for each UI, we take a section SI in F of UI. So we pick a section in the pre-sheaf. Now, suppose that for all A, such that this diagram commutes, which essentially means that A is a common, lives inside both UI and UJ in a sense. If we want to see it in a different way, if there are pullbacks in this category, then this pullback will be the intersection of these two, and then A will factor through the intersection. So essentially this tells us, if we prove what I'm about to say for all A's of this type, we are proving it on the intersection without saying that we are working on the intersection. Okay, so whenever we have a commuting square of this form, we can restrict both functions through the two inclusion maps. And suppose that every time we have this square, these intersections agree for every couple of I and J, then we call this a compatible family. The meaning of this is precisely what we were doing before when we intersected, and we were saying this section restricts, both sections restrict to the same section in the intersection. Okay, what does it mean to glue these sections? It means that there exists a so-called amalgamation. What is an amalgamation? It's a section on the total space, so the covered space, S, such that for every I, if we restrict S, this coincides with SI. So this is what the gluing will be. Okay, so now the definition of sheaf is relatively easy, because we say that pre-sheaf is a sheaf if every compatible family admits one and one only amalgamation. So this is exactly the lifting of what was happening before. Okay, now we denote by sheaves over a site, we denote the sheaves over a site by this notation, and it will be a full subcategory of the sheaves. So maps between sheaves will be maps of pre-sheaves. Okay, and now the first definition of topos. So what's a Grothendieck topos? It's a category which is equivalent to a category of sheaves over a small site. This is what a Grothendieck topos is. So in particular, given the examples we saw before, for every topological space, the space of the category of sheaves over this topological space is a Grothendieck topos. If now we take the trivial, which I recall was the coverage, where the only arrow that covers an object U is the identity. So the most disconnected, the one I call the most disconnected one. And it turns out that, yes, this is the most, has no relation whatsoever between local to global. So this is exactly pre-sheaves. So pre-sheaves are also a Grothendieck topos. And this in particular this tells us also that the category of sets is a Grothendieck topos, because of course, if we take as a category C the terminal category, then pre-sheaves are, this category is isomorphic even to set. Okay, on the other hand, if we take the empty coverage, which I recall was the coverage where the empty map covers an object, every object U. What happens here is a sort of logical trick, because every time we use the universal quantifier on an open map, then this is an empty condition because everything works. But that's not the case for the existence. So what happens now is for every compatible family, there are no compatible family. I mean, we can take the empty family, so there is nothing to quantify on. So this is an empty condition. Empty, there exists one and only one element S in f of U, such that the restriction condition, which works for all elements in the category. So another empty condition. What does this become? Becomes exactly, there exists one only element S in every f of U, which means that the only object is the one. So that's why this is a category that is not interesting in a different way, the opposite way if we want. Like this is the biggest possible Grothendieck topos with a fixed site, and this is the smallest. Okay. So if we fix, we start from the data of a site. Site is a category and a coverage. But it's not true that different coverages produce different topoi. In general, there are many, the data that we give through a coverage is the minimum data that then generates sheaves. But this implies that there are a lot of families of functions that do not belong to the coverage, but still behave as if they belong. So they still satisfy the sheaf condition, meaning there are families that are not in J, such that they behave as if they were covering, which means they have a notion of compatible family, and every compatible family glues for every sheaf to a Okay. So this is the analog of the classical condition of the refinements. And so, okay. And now, how do I? Okay. Okay. Back. Okay, and now it's back. Okay. Yes, so properties as a category, properties of a Grothendieck topos as a category. So first of all, I said that a Grothendieck topos is, well, let's say, a category of sheaves is a full subcategory of the category of pre-sheaves over the same category. But it turns out that this inclusion has a left adjoint. So this is what's called the reflexive, I think, inclusion. But so there is a canonical way, and it's left adjoint to the inclusion, to transform a pre-sheaf in a sheaf, and this is called the sheafification. This is a technique to produce sheaves from nothing. Now there are other properties. It has all small limits and colimits. In particular, then it has products and the empty product, which is the terminal object. And then it is Cartesian closed, which is what I was mentioning before when I said exponential object, which is this object. So what it means is that the functor product by an element is naturally isomorphic to the, it has a right adjoint essentially. What does the right adjoint represent? It wants to be an internal interpretation of functions. Why? Because if we interpret it as using the mathematics that we use every day, like every time we have a situation like this, it means that this part, so we have a parametrization of functions from x to b, and this is what it wants to represent. Just an idea, but yeah, so it's an internal object, internal to the category, that wants to look like functions from x to b, morphism from x to b. It has this property. And now there is one of the main properties of toposes, topoi, which is the existence of a subobject classifier. What is it? It's a morphism, T, and we'll later see why it's called T, not by chance. T from 1 to omega. So in a sense, it's a point of omega. So T is a point of omega. Omega is an object of the category. What is this object? It's an object that represents the functor of subobjects. How? Given a subobject, there exists a unique map from subobject of C. There exists a unique map of C into omega, such that the pullback through the morphism T that we put there gives us exactly the subobject. So every subobject can be described as a pullback of this map, the T map, to through a map from the object to omega. How do we interpret this? The idea, if we look at the category of sets, which is a Grothendieck topos, and so it meets a subobject classifier. The subobject classifier is, so the omega is 2, and the subobject classifier is the T that selects one of the two elements. What does this mean? It means that phi of u is the characteristic function, essentially. So if we have a subobject u, we define on C the characteristic function that is f when the point is in u, and t when the point is in u, and f otherwise, and this gives us exactly what we want. Okay, so this is what happens on the sets. So given these properties, actually, people noticed, and I think it was Lovir who passed away a month ago, I think, more than a month ago. And the idea was to find the minimal properties that enable us to do what we are going to do for the rest of the talk, essentially. What are these properties? So we don't need all limits and colimits. We only need finite limits. We need Cartesian closeness. This is essential because we want to model functions inside. And we want the subobject classifier. So these three properties are all that's needed to do everything that we're about to do. And this is what's called an elementary topos. But whenever I say topos without any adjective, I'll mean this one. So examples, any Grothendieck topos is an elementary topos by the properties I mentioned before. The category of finite sets is also an elementary topos, but it cannot be a topos because, as I said before, every Grothendieck topos is also co-complete, which means I can take the discrete sum of one with itself an infinite amount of time, and then I will get an object that can't stay inside. Is it working? Yeah. Yeah. Well, it's also a sheaf on a compact, but but then it coincides with the sheaf of continuous motion. If it's not, then it's not a sheaf. I don't know. I mean, I don't know. Maybe with some weird gluing. I don't know. I don't have an answer. Is the microphone working? Hello? Okay. Good. Okay, so this is what generators are. And yeah, with Grothendieck Topos, we have a set generator. Good. Yeah. So properties of elementary topoi. So we only ask for finite limits, but surprise, we also have finite co-limits. And in particular, we have finite push-outs and an initial object. Initial object, which will be in Grothendieck topoi is just the empty set on each component. Okay. And now other property that holds for elementary topoi, the set of sub-objects is a Heiting algebra for all objects. What's a Heiting algebra? First of all, it's a poset, and we know it's a poset because we have inclusions between sub-object in any category. It has a top element and a bottom element. Okay, that's the total space and the initial object that embeds. And then it has finite meets. A meet in a category of in a poset category is the product. So what's the property of the product? If we translate the categorical universal property to poset property, it becomes that for every two arrows, there exists a unique arrow to the product, which means the product is the biggest one such that it's contained in both U and V. This is what it means. So what do we take? We take the pullback. We have two sub-objects. We take the pullback, and that's the meet. We also have joins that are co-products. So we reverse the previous notation, and this time it's the smallest sub-object that contains both U and V. What do we take? We first take the pullback, and then we take the push out of that. And that's the meet. It's the push out of the pullback. And then we have this object which really characterizes the Heiting algebra, which makes them the key for studying intuitionistic logic. And it's a map called implication. How does it work? What is it? It wants to be a right adjoint of wedge. So in particular, we want this category to be Cartesian closed, which means that this is the exponential object that we were looking for before. How do we build it? We build it as, so we want it to be the right adjoint of wedge, right? So we put the wedge on the left and the map on the right. And what this property means is that the implication U implies B is the biggest object such that whenever it happens that the implication is true and U, which is the hypothesis, is true, then V is true. So this is what the implication means. Whenever it is true and the hypothesis is true, then the thesis is true. So we want the biggest possible. Whenever we have this so far was these are the axioms. This is all. An extra property that we get is the existence of a negation that we can define by U implies 0, which is the bottom element, and therefore it wants to represent false. What does it mean? So let's substitute the 0 in this one instead of V. This is what happens, but now no element is less or equal than 0, so we can actually put an equal here. So what this property means is that not U is the biggest possible element such that intersected with U gives 0. And it turns out that it's no more true that not A is A, nor it is true that not A and or A is truth. So the excluded middle is not true anymore. And this is what we are working with. Okay, more curiosities about the, I think, algebras of subobjects. Whenever we have a map from X to Y, we have a pullback map from subobjects of Y to subobjects of X. And the way we obtain it is through the pullback, like not by chance, the name was given. What happens is this map has also right adjoint and left adjoint, and we call them, again, not by chance, existence and for all, exists and for all. Why? So we want them, let's start with exists. We want it to be left adjoint, so we put it on the left, and we have on the right the pullback. And same, but in the other way with the for all. Let's see what it means. So first of all, they are adjoint to the F star, so it goes from sub X to sub Y. Then let's study in particular the only case that we will use, which is the projection, the case where F is a projection from X times Y, which is this square, to Y. So we forget the information of X. Okay. Okay, so now the pullback takes an element in space in Y and brings it to the whole stripe above this space. What this means, existence, is we take a space, which is the blue one, for instance, take the blue one, and we want to find the smallest element such that its pullback is contains entirely U. It means it's a space in here such that its pullback must contain the whole of it, and it must be the smallest, so it's the green. Why now do we call it existence? Because it means that it's the set of elements in Y such that there exists an X for which XY belongs to the set. The same happens with for all. For all is a right adjoint, so this time it must be the biggest one, such that the pullback of it is contained in the space, in the original space. So yeah, this is basically the biggest possible that I can take. Yeah, here the color is not great, but the biggest possible that I can take before going out. If I take a bit more, I get a piece of gray. Okay, again, why is it called for all? Because it's the set of points here such that for all x's in here, the point x, y belongs to the blue space. So this is why they're called the exists and for all. And we'll use this property precisely as a way to interpret these two logical symbols in our theory. Okay. And now we start with logic. Now it's time to, yeah, now it gets dangerous. So let's define a many-sorted language. What's a many-sorted language? It's a list of symbols that are sorts. What's a sort? So it wants to represent the type of variable that we are using. For programmers, it would be something like floats, integers. For us, I don't know, for instance, if we want to model the theory of modules, we need something that represents the ring. So we'll have a sort of ring. Exactly. We'll have a sort of module as well. And these are the two symbols that will be our sorts. That's all we need. Then for every sort, we need an infinite set of variables. These are just placeholders. They're just names that we need to know that we can put stuff in. and we know when they have to be the same. Anyway, so they're variables, the way we're used to deal with them. Then for every sort, there can be a set of constants. And constants are some specific values that we want to assign to, like, I don't know, for our theory, there might be the need of some constants. For instance, in the theory of modules, we need a zero, which is a constant in the ring, but we also need the unity, we need the zero of the module. So these are all constants, for instance. And now for every group n+1 tuple of sorts, S1, Sn, Mt, we can have function symbols. Function symbols, which will be denoted this way with the comma between the first ones and semicolon for the last one to denote that these will be the wannabe domain and this will be the codomain. Okay, example in our case are the two operations on the ring. So these are from R. They take two elements in R and they give us an element in R. This is the sum on M, and this is the action of R on M. This is it. Okay. And finally, we need for every n tuple of sorts, so we need relation symbols. We might need relation symbols. In the theory of modules, they're not necessary, but let's assume we want to model ordered modules, then yes, then we'll have to define an order on the module and so on. And that will be less or equal of type of sort M. Okay, so this is a language. Language meaning it's only the alphabet. Now it's time to put the alphabet together to create words. And now you see why I like this subject. Right? So given a language, we define a term T of sort S. So terms always have a sort associated to them. And we denote it by T colon S. And we define them inductively. So the atomic terms are variables and constants. For every variable, we define every variable is a term of sort S, and so is every constant. And then given terms, like terms that we have already built using atomic pieces or other inductive properties, given these terms and a functional symbol such that the sorts of T1, Tn agree with the domain sorts, we get a term called f of T1, Tn of type the codomain of f. Okay. So this is what it means. Where? This one. This one is T because this is also T, unless I messed up. Ah, I see. Yeah. Okay. Yeah, it was thought as disconnected, but yeah, true. Yeah. All right. Yeah. Then yes. Term of. Sorry. Yeah. Term of sort T. Yeah, exactly. These are three ways of building terms of sort T, and this happened to be a term of sort T. But yeah, S is the real term. Yeah, my mistake. Examples. Given variables X and Y in the sort of ring and the V in the sort of module, we can build this object by combining together two terms in R with a function that takes values in R function, I mean a functional symbol, R and gives an object in R, then I combine it with an object in R by the multiplication. So this is how I'm building it. And of course we can rearrange in the usual way so that it's readable by humans. But what we cannot do is to undergo simplification because this term is different from this term. We know that the rings have all sorts of properties with the neutral element to the multiplication, but they are different terms. They might have the same interpretation, but yes, but they're different. So now that we have words, we only need to build sentences. So sentences in logic are formulas. What's a formula? Again, we build it by induction. We know that those two symbols, which correspond respectively to false and true, we know that those are formulas. Then whenever we have a couple of terms of the same type, and it's important that they're of the same type because otherwise they won't be comparable, they wouldn't be comparable, then there is a formula T1 equals T2. Then given a term, n terms, and a relation symbol, then if we plug in the terms in the relation, this will be a formula, so on. Yeah, then if we have two formulas, then we can use the logical operation that we saw before. So we can build the formula phi and psi, phi or psi, phi implies psi and not phi. Being done this, we now take a formula that contains x as a free variable, which I'll explain at the end of this sentence. Free variable x of type S, then also these two are formulas, and I read them for every x of type S, phi of x. And at this point, in this formula, x will not be free anymore. So what does free mean? Free means that it's not bounded by universal or existential quantifier. So it's like the integral symbol, essentially. So if it's a free variable, I can plug in values, but if it's under the sign of integral, and I'm integrating through that variable, then I'm not allowed to change the value because it has another meaning now. Okay, this is it. An example, this is distributivity, and it's a formula, and it's a formula without free variables as well, because I'm saying for all x, I'm saturating all the variables. Okay, good. Okay, now we have a language, but it's completely devoid of meaning. Yes. Yes. I see. Yeah, those are the tricky parts. Yeah. Let's see. How was the solution? So I think that you quantify for all instances of the same variable. That's the trick. So it can't be that like you're quantifying over. I see. Like you mean if I do for all x something in x and then end x equals x, something like that. Yeah, that's not allowed, but those are tricky things that I have not mentioned. Yeah, so technically you shouldn't be able to use bounded variables, let's see. And the fact that we have infinite variables and the fact that all formulas are finite means that there will always be a variable that we can use. Okay. Yeah. Okay. Okay, so I was saying we now have a language, but it's completely devoid of meaning. So what we are doing now is like the golem of Prague. We are taking the words and we are putting them in objects of this category to give them meaning and to give the language itself a meaning. We give a name to the objects and we give a meaning to the language. Beautiful. Okay, so we have a language. What's a structure? Structure is an interpretation of the language. So every sort will be interpreted as an object in the category. So a sort of ring will become an object in the category, and then we'll build them. Every constant will become a point, and as I said before, points in category theory are just maps from the terminal object to S, and of course, I'm requiring finite products, which also implies the existence of one. Then for all function symbol, every function symbol of this form will be interpreted as a morphism from the product of the interpretation of sorts to the interpretation of the final sort. And then for every relation symbol, we interpret this as a sub-object of the product of the interpretation of its sorts. Okay. Now we need to interpret terms. So we have interpreted the words. Now we have to understand what words are. It's the same trick over and over. So we build it again by induction. The variables become the identity. The constant are just interpreted as we interpreted them before. Now, if we have a term defined as a function of other terms for suitable f, then what we do is we take the interpretation of the function, which has this as domain. We consider the product of arrows that map the variables of the term T1 and from T1 to Tn into Si. So we take S, which goes from the product. We make the product of the interpretation of terms. We obtain a map from here to there. The only missing thing is to apply this sort of diagonal map, but not really. The reason for this is in here. So what does this mean? So T is made of this, which means the variables of the Ti's are contained in the variables of T. What matters now is that every variable appears only once. So I can't take two sorts if the sort is appearing with the same variable. So what I do is I take all variables and I map them, I project them to the variables of each term so that I forget the variables that are not necessary for T1. In this way, I'm sure that I will not have double interpretation. And then I take the product of this map, so I use the universal property of the product to build this map. And throughout the interpretation of forms, it will be the same. I will not stress this point anymore. I will just say that after bringing everything to the same object of variables, things will work. There will be a lot of pies, not only because today is P day, but because it's necessary. Yes, it was the only way to put a pie inside the posterior. I wasn't able to find a better way. Okay. Now formulas. We have a formula with 3 variables like that. We will simplify by denoting FV, the interpretation of FV as the product of the sorts of the 3 variables that appear in the formula. And we interpret the formula as a sub-object of the 3 variable. Now, what does this mean? We have to think about set theory. How do we interpret a formula in a set? The way we do it is we take, so the formula has certain 3 variables, which means I can plug in values, and the formula will tell me if this value satisfies or not the formula. The values I'm taking them in the total set, which is the interpretation of FB. And phi will represent the sub-object where the formula is true. So this is what the formula represents. We'll be a bit more specific about this later, but now just to allow understanding of whatever comes. Okay, the truth is interpreted as 1. So there are no 3 variables, so it's the product of nothing, and it's 1. It's the total subspace. The bottom is the empty subspace, or the 0, the initial. If a formula is an equality, then what I do is I take the 2 terms, and now you see why it was important that they landed in the same place. The 2 terms, I put them under the same space of variables, and then I take the equalizer of these 2. And it makes sense that this is the formula phi. Okay. Then if phi is relations over certain terms, what I do is I take the terms, I bring them under the same set of variables, And I use the universal property of the product to define a unique map from here to all sorts. Now the relation lives inside the product of sorts, and lives inside as a sub-object, which means if I take the pullback, I also obtain a sub-object, and that will be the interpretation of my formula phi. Now, given formulas phi 1 and phi 2, I can interpret the end or an implication as the corresponding objects in the Heyting algebra that I defined before. So I first bring them under the same set of variables, and then I make the meet in the Heyting algebra. Okay, then we interpret not as the interpretation of not phi is not the interpretation of phi. It is, but it's defined as not the interpretation of phi. And now, yes, when we have a formula that has a free variable x, then we can define these two. Here, notice that it's exactly the situation I described before, because the free variables of phi compared to the free variables of psi compared to those of phi contain one extra element, because phi has x as a free variable and phi does not. So this is the extra element, and the projection is exactly forgetting about this part. So we know that the exists and for all correspond to the notion we want of exist and for all, the ones I showed before, the Heyting algebra. Okay, this was necessary. And now back to the interesting part. So we said that we interpret formulas as sub-objects of the interpretation of the free variables. Thanks to this idea, we can use this notation instead. So instead of writing interpretation of phi, x1, and so on, we write it in this suggestive way, which shows us the comparison with set theory. Here we can really see that if we take, instead of a generic topos, we take set, then this object, this formula is exactly the set of x1, xn, such that the formula phi is true. So this is useful to keep in mind. Yeah, exactly. So as I was saying before, the interpretation of formula phi represents the part, the sub-object of fv phi that satisfies the formula phi. In particular, a generic formula is true if this subset corresponding to phi coincides with the total space, which means everything satisfies the formula phi within the free variables. Okay, now in particular, if a formula has all variables that are bounded, I mean no free variables, this formula is called a sentence because it's a statement, it's a generic statement about mathematics. Like it doesn't depend on parameters that you might plug in here. So what happens, as I said, it's the interpretation of the empty collection of free variables is the terminal object, which means a sentence is just a sub-object of one. Now, what can happen in set theory is not much, because sub-objects of the terminal object are just the empty set and one set, which correspond to 0, false, and true. So the way we interpret it is the sub-objects of one are the different ways a sentence could be true. So they are truth values. And the only true value is truth. Now, okay, I will be more specific about this, more clear, hopefully. But what matters is that, okay, sub-objects of one, which correspond to values of sentences, correspond by the definition of sub-object classifier to maps from 1 to omega, which means points of omega. So the omega of the sub-object classifier has as points the truth values. So omega is the object representing truth values within the topos. More. Exactly, represents possible truth values within the topos. And in particular, the point that we selected via the subobject classifier, the T from 1 to omega, this corresponds to truth. This is the truth value true. It's the only true one. Yeah, no, exactly. Then in particular, we can also build the false, for instance, which, so since every object intersected with the truth is that object, the only object that gives the empty is the 0. So we know that not true is also false. So this is the definition of false. But more, we know more. So we know that the sub, and I spent a few slides to talk about it, is Heyting algebra. And I also described the pullback, which defines natural transformation, a natural way of, a sense of naturality in the sub, let's say. And we know that this is a natural isomorphism. What this means is that this functor is representable with representative object, the omega. But what Yoneda's lemma gives us more is that every Heyting algebra operation on this functor translates into an internal Heyting algebra operation here. So we had a way of taking joins, meets, joins, implication inside of this Heyting algebra. This translates into an internal morphism in the category from omega times omega to omega. We have truth values. One is the true, one is the not true, which is false. We have a relation because we know that Heyting algebra is in particular a poset, and this gets interpreted in a strange way as a relation. And the way we deduce this is through the fact that the poset structure actually can be recovered by the algebraic operations. But anyway, we have this relation, and what this represents is an internal Heyting algebra. What do I mean? Let's take the sort of Heyting algebra, and let's call it omega. Then Heyting algebra, if we want to talk about the theory of Heyting algebra, we need everything that we use to describe the properties, right? So we need this guy, this guy, this guy, symbols denoting these guys, this guy, this, and this guy. We have these objects, and we know that they have to satisfy some property. Properties, what are properties? They're formulas. So what this means is that the object omega, if we interpret the language, the sort omega as the object omega, and the symbols corresponding to these functions as exactly these morphisms, what we get is an object for which the axioms of Heyting algebras are true. So this means that if I'm living within the logic of Topos, this for me is an internal Heyting algebra. It's delicate, but yeah. Anyway, and then we also get the no. Okay, so now we define a language, we define the interpretation of the language. Now we need to understand what this interpretation is. What does it mean? So if we are in set, the interpretation is kind of easy, meaning that it's everything that we are used to. So logic itself is modeled on it in a sense. So if we want to interpret something, we just check the set, and the fact that the subset of the formula completes the whole set will tell us if the formula is true or false. Like we know everything in set. In Topos, it's not like we need to find a way of understanding when a formula is true by induction, for instance. So I don't know, we have a formula that's built of several things. We know that we build them by induction. So at each step, we need to understand how to deduce truth from the lower steps. So if a formula is made of other formulas, we want to know when the big formula is true. We need first to understand when the two small formulas are true, and then how to interpret the truth of them as a truth of the generic one. Okay, didn't make much sense, but we'll see if afterwards it makes more sense. Okay, so in set, how do we check if a formula is true? We take a formula, we substitute a value, x, in x of type x, which means a point, an element 1 to x, and we evaluate the formula at that point. The value of that formula will be true or false, and that will tell us if the formula is true there. And then we'll take the set of all points for which the formula is true. This is how it works in set. Why? The reason is, as I said at the very beginning, 1 is a generating element for set. We don't have this luxury in all topoi, elementary topoi. So what do? We take a generalized element. Instead of fixing only 1, as I said also at the very beginning, a solution would be to take every possible object, u, and evaluate the formula at this generalized object. What it means is I'm not picking a particular point, but I'm saying, let's assume I'm starting from the point of view of u, and I'm entering x, which could be also a space entering an open entering a space, for instance. And I will see if under this open, the statement will be true. This is more or less the interpretation. It's clear. But anyway, once we have this generalized object, we say that the formula phi is satisfied at the generalized object alpha from u if this map factorizes through the subspace where phi is true. So this is the generic interpretation. And we write u, this is called forces, u forces phi of alpha, but it can also be read as phi is satisfied at u on alpha. Okay, so this is the Crick-Joyal semantic, and this is a way of like using this general principle. We have a way of deducing truth of certain statements from of certain formulas from formulas that build this formula. But they are quite complicated and not maybe not as intuitive as what happens in a Grothendieck topos. So let's go back to a less general situation. Why? Because now we have, as I said also at the beginning, we have a set of generators. Generators which are sheafifications of Yoneda. So every object in the site corresponds to a generator. And we know that two maps are the same if they coincide on all generators. So yes, now the idea is to take elements of this form and use them to classify everything. But now what happens? Let's take an element of this form. So it's a map from the sheafification of Yoneda of U to X. But we know that the sheafification is a left adjoint, so this is isomorphic to homomorphisms of pre-sheaves from Yoneda of U to X. But what this means by the Yoneda lemma is that alpha corresponds exactly to an element in X of U. Okay, so now the situation has changed, because before it was a situation inside the category where I had to map arrows and check categorical combination if they agreed or not. But now the situation is different, because now I'm working again with sets. This is a set again. And this is what makes the interpretation in Grothendieck topoi a bit more, let's say, computable. So let's see. We write U forces phi of alpha instead of this. So we forget about the functor. We start the Yoneda functor, and we go directly to the object that this functor corresponds to. And we say that an object on the site forces the formula if this happens. If the unification of the unit forces the. Okay. And now, and a formula is true if it is satisfied by every element at every object U of the site. So this is now the interpretation. Now we are really able to say when a formula is true. And there are rules. So yeah, there are rules to deduce from a composite formula. So to deduce a composite formula from basic formulas, from information of basic formulas. And so we would expect something like the top one, right? So we have, let's remember, U is a sort of point of view. And we need for something to be true, we need it to be true under every point of view. Makes sense? We expect that phi and psi evaluated at alpha is true if and only if it's true that both phi and psi are true, right? The first one is exactly what we expect. So in sets, so that's what happens. A formula is true on an element alpha if the first one is true on alpha and the second one is true on alpha. But if we look at everything else, basically nothing really behaves like that. We can group them in families. The red ones and the red ones work in this way. So something is true if there exists a coverage in the extended sense. So it could be also something generated by the elementary one. If there exists a coverage such that when I restrict my alpha through each element, each UI forces phi of alpha restricted there, or the other. So basically, whereas the end was just the evaluation at the set itself, the or becomes we want there to be a coverage where for each element the or condition is true. And the same happens for the existence. Also there must be a coverage such that there exists an element, but on the smaller bits. What happens instead of on the blue ones? On the blue ones, it's something else. It's a for all instead of an exist. It says for all V that enter in U. So every time I have a map from V to U, we have that the restriction on the restriction, the statement is true. Okay. And then we have something in between that uses both the for all maps and the coverage bit. Okay, why this heterogeneity? The thing is, it's a trick. Actually, they're all the same generalization. They are both, all of them are of the form. Let's take an example with the and, but it works for every other thing, every other combination of formulas. U forces and if and only if for all functions entering into B, there exists a coverage of V such that the formula is true on the domains of the coverage. So I want for a formula to be true in a spot, I want it first to pull it back through everything else. And then on everything else, I need there to be a coverage for which on each covering space, the condition is satisfied. So why then in the previous one, some had one property, some had another? The thing is, some are not necessary. So I can assume the same condition for all of them. And what I get is that here the right condition is not necessary because whenever I have also the right condition, I also have it on the covering part. And here the opposite. So whenever I have it on the pullback condition, let's say the monotonicity condition, then I also have it on the total space. So this would be the true form of all of them, but they happen to be simplifiable in the other way. And now to lift a bit the spirit, I can give a sort of a feudal interpretation of how this works. So what does this mean? Just to have an idea. we interpret so first of all, we said that a formula is true if it is true on each object of the site. So how do we interpret this? We take the site, which is some form of some group of people that have a decisional power. So the element U are the politicians. Good. So what does it mean for, this is not canonical, by the way, this is just an interpretation to lift up the spirit because it's been quite a while. What does it mean for you, for a formula to be true on alpha? It means that U declares the formula to be true, even though he sees it in a different way. That's what politicians do. What does it mean that U goes into in the site? It means that U is a subordinate of V. Okay. How does the decision work? Okay, so first of all, we have a site F, and the way U sees F, the real way he sees it, is through this set. This is a set, so here we know if a formula is true, false, we know everything about it because it's classical logic. So this is how he sees it. But the way he replies to the answer is, first, I look at all my subjects, and this is the first part, for all V for U. Okay, maybe I should. First, I look at all my subjects, and then I need to interpret the coverage. What's the coverage? A coverage of V will be subjects that are supporting V. So for every subject of U, a covering family will be a supportive set of subordinate. So how does a decision take place now? For every subordinate, we look at all his supporters, and if they agree that something is true, then I can say that it's true. This is how it works. It's kind of funny. What do you get through this interpretation? And that's funny as well, because we have for every time we have a subject, so V is a subject of U, then what we get is whenever U says something, also the subject says the same thing. Nice. But also that like politicians need to stay in power. So if there are enough supporters that say something, then also the politician must say it. And these are the two properties. And now back to geometry. What do they represent? The first one represents monotonicity. So if every property that will be interpreted in the Kripke-Joyal semantic and the logic of Topos that is true in on an object will also be true when restricted. So this is the first property. The second property is that everything that is true locally in a way that the information on UI covers the whole space, then if they say it's true, it's also true globally. How does this translate better into geometry? If the theories are simple enough, and by simple I mean they only use algebraic expressions and not quantifiers, or like basically if they don't use too much higher logic, let's say, then it behaves very well. So what's a group object? So now I'm taking the object group, the sort of group, I'm taking the theory of group, and I'm asking an object to satisfy the axiom of group. So I need in the Kripke-Joyal semantic or in the political semantic to something to satisfy. So the council must decide that this is a group. A group object becomes a sheaf of groups. Same for rings. A group, an internal ring becomes a sheaf of rings, and so on. With fields, it's different because fields require the not condition because you want the invertibility for everything but the zero, and that's different. But so everything generalizes. Everything, easy thing generalized, less easy thing generalized to some more complex thing. For instance, something more complex. So here the notion generalizes, but here the notion becomes local. So something that was true on every component now, it's true in Kripke-Joyal if and only if it's true locally. For instance, a finite presented module object in a topos of sheaves becomes a quasi-coherent sheaves. But this is actually good news. I mean, it seems like it's getting more complicated, but there's an extremely good news, which is this logical theorem of soundness and completeness, which tells us that if we consider a language and a formula and everything, then the formula is provable in intuitionistic first-order logic, if and only if it is valid in every elementary topos. What does this mean? It means that everything that I prove intuitionistically about, for instance, finitely generated modules, which have a sort of easier theory compared to quasi-coherent sheaf, will give us for free a result in about quasi-coherent sheaf. I will just have to take the same statement that I formulate in first-order logic, intuitionistic deduction, and everything. Same statement, translate it through the Kripke-Joyal semantic, or I use the internal language and I interpret it there. And this theorem of classical algebra will translate in automatically without any proof needed to a theorem of about quasi-coherent sheaves. But there's also the other way around that can be exploited. So if I manage to find a topos weird enough that a property doesn't hold, it also means that we will not be able to prove it by intuitionistic logic, which is how certain things have been proved, like the independence of the continuum hypothesis from Zermelo-Frankel. The existence of a discontinuous function apparently cannot be proved by, like, there exists a topos where every function from R to R is continuous. And when I say continuous function from R to R, I don't mean that we take an object R. No, I mean we build R from natural numbers, rational numbers, in Dedekind sections. We define a continuous function with the formula for all epsilon, blah, blah, blah. And the notion of continuous function will be true for every real number object, to every real number object. And finally, the axiom of choice also is cannot be proved from the rest. Thank you. Sorry for the time.
Are there any questions?
Okay, just go back to the last slide. Okay. Yeah. I guess like also selection choice, these can't be proven even intuitionistically, right? Like,
yeah.
So,
but in particular, this is just for the intuitionistic part. Like there is a proof, like you build a topos where I think the condition was that not all epimorphisms are split epimorphisms. I think it translates in something like that. And that's how you prove that intuitionistically you can prove it. But it's not a full proof of the independence of the, it's an intuitionistic.
Yeah, because I mean the discontinuous function, I mean that surely it has to be intuitionist, right? Because if you're allowed to do things normally, then you can of course define a discontinuous function, right? Yeah. So I also just really so you show how to sort of interpret all this logical stuff in a more categorical way. Can you also do other things that you do in classical model theory, like take ultra products and prove some kind of Washes theorem?
So in a sense, that is a kind of, it's not an ultra product, but it works in a similar way, right? Because also in the ultra product, you have a set of people that make decision. And if it's big enough, which means if it's in the ultra filter, then you have a decision. So I would guess that is the generalization that can be seen in the same idea.
Nice talk. It's a question a bit in the spirit of your first slide. So, pourquoi, meaning from some geometrical motivation, and I will try to answer probably by myself, and you will try to correct me. So am I right that it's a way to prove things if you have some theories that have a good localization,
Mhm.
and then you look at this localization, it looks like some familiar objects, I don't know, from sheaves, groups, or whatever, and then you have a strategy how to prove your the similar statements in your complicated theory, or
Yeah.
okay, that's it.
You start, yeah, I mean, like for instance, where if we take like these objects that generalize in a nice way, then automatically, I mean, we don't need to go through the idea of local, like proving that it works locally and everything. So it gives for free all statements about groups, rings, objects. So it's, I don't know if I got that.
Behind geometries, the next one will be probably super geometry, which is natural language for that will be representable functors and stuff like that.
Yeah.
As I understand, you can easily apply these things to super stuff and get the proofs from I don't know, algebraic geometry for free.
Yeah, maybe.
Okay, it's also a very vague question. So, but am I right that you kind of need some good localizations property, right?
Yeah, exactly. And in fact, I was thinking about the notion of localization for non-commutative calculi and exterior algebras. And my wild solution was, how about we forget about what should be a nice space? Like we start from the exterior algebra and we want to build a space that gives a notion of localization. How about we forget about that and we take a generic site? So the most generic possible notion of locality. And then we take an exterior algebra object with the internal logic. At that point, that sheaf, when restricted to every object, will be an exterior algebra. So that's exactly what we want. The problem is now the notion of locality is completely separated from the exterior algebra. So my idea might be to use that to understand how the sieve should be done. I don't know.
That you also suppose that in your series there is enough of exponential functors, whatever it means.
Yeah.
In this
topic,
topic,
we need every topos has the exponential functor. Every two object can be.
I think that's the main problem in non-commutative geometry is most of the functors are not exponential.
Also in differential geometry.
Yeah.
It starts getting wild pretty soon because spaces of functions can be too big.
Okay, thanks.
Yeah. Yes. Yeah. So there is a notion in between which is called the Bohr topos, but I'm not able to understand it at the moment. But it puts together the two things. I don't know how, but I think it's the common ground. Yeah, I think it's. But again. Yes.
Okay, also a very naive question. When you say group, ring, or module in a Topos sheet where each component is a group, it means that the small category, each object is a group, or
No, it means that so a group object in the category would be G over the site, so G from C of two set. And so what it, spoiler, what it turns out to be is actually G goes into the category of groups. That's
Okay,
what
it
I
was my
meant.
question. If
Yeah.
you could change set for
Yeah,
another.
that's exactly what the last page wanted to say. Basically, if I take, I'm working in the Topos SH, C, J. I'm working in this Topos, and using the internal logic, I say what it means to be a group. Turns out that what it means to be a group is exactly that this sheaf factors through this category, through the forgetful functor. Same for rings and everything that is algebraic enough. Yeah, then that's also a group. Yeah, it's a one-to-one correspondence. And this works very nicely, as I said, for every algebraic thing. So. Then they become local. Everything that you formulate becomes, there exists a covering map such that for all reduction, that property holds, something like that. By the way, I think I haven't said, which maybe I was, why did I take first the for all V and then there exists the thing? Couldn't I do the other way around? Turns out I can, exactly because of the definition of coverage. Because that factorization is exactly this. The beginning is the end.